Good morning, everyone. Thank you once again for joining us in our De La Salle IALU LaSalle Sustainability Lecture Series. So together with me is Ria Sumaga, who will be co-moderating today's session. Good morning, Ria. So for those of you who are joining us for the first time, so kindly keep your microphones on mute. And if you have any questions, you may type them in the chat box, which you can find at the bottom of your screen. And we'll get to your questions at the end of the lecture. Before we begin, let us start with an opening prayer to be led by JR. JR?
Morning, everyone. Let us put ourselves in the most holy presence of God. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Father in heaven, God of love, all I have and am is yours. Grant that I may become a living sign of your compassion in this world. Grant me the faith to live my life, always in the awareness of your loving presence. Grant me zeal to serve without thought of reward those to whom you send me. Grant me charity to bear the burdens of my brothers and sisters. Teach me to seek your Son's face in the last, the least, and the lost. In whatever I undertake, may I seek above all things to procure your glory, as far as I am able and as you will require of me. Strengthen me by your Holy Spirit to follow Jesus by living the commitment I make this day. Amen. Our Lasallian prayer, I will continue, O my God, to do all my actions for the love of you. Saint John Baptist de La Salle,
pray for us.
in the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Thank you for that, JR. Now to give us the opening remarks, I'd like to call the Vice President of Research and Innovation of De La Salle University, Manila, Professor Raymond Tan.
Thanks very much. Let me share my screen briefly. First of all, good morning, good evening, or good afternoon to the participants of this 16th installment of the Sustainability Lecture Series. This is a lecture series which was launched in the early days of the pandemic as part of our university's thrust to focus research and sharing of ideas towards the joint goal of making lifestyles more sustainable for the future of this planet. This is actually a series which was conceived and sustained over the past year and a half to date, in cooperation with the International Association of LaSalle Universities, which is a global network of kindred institutions, all tracing our roots back to medieval France. This is work which was supported by our representative to the IALU Research Committee, former Chancellor and current Chancellor Emeritus, Dr. Carmelita Quebenco, and of course my colleagues, our host, the Dean of the Gokongwei College of Engineering, Dr. Kathleen Aviso, and the Director of the Center for Engineering and Sustainable Development Research, Dr. Alvin Colaba. And the intent was to provide a platform for sharing of ideas, not just within the LaSalle network, but in fact, within the regions where the network has presence. And I'm glad to see that we do have quite an extensive intercontinental participation in today's event. Now, the lecture series traces its roots back to two important documents, which became public knowledge in the middle of the previous decade. For the Catholic world, the Laudato Si encyclical of Pope Francis provided a global call for reconsidering the way we live our lives and looking more carefully at how to care for the planet. And at roughly the same time, of course, the United Nations Sustainable Development Goals provided a more secular framework, but towards the same end. And I'm glad to note that if we look at the SDGs in particular, today's talk deals with the second SDG, ensuring food security. And what we've done so far over the previous 15 lectures in this series was to have a diverse set of speakers, typically on the last Wednesday of each month, but we've had to adjust the schedules at certain points. We live stream via Zoom, and for those who are unable to join the live lectures, there's a YouTube recording which is released several days after the initial event itself. And we've dealt with diverse topics, all of which just relate to sustainable development. Definitely, these are driven by the interests and the expertise of the speakers themselves. We've also considered alternative formats, for example, alternative languages. And in fact, today we're happy to note that this event, which is the result of transdisciplinary, intercontinental, and gender balanced research collaboration that we can trace back to 2019, is also going to be delivered in 2 languages, in Spanish and in English. And of course, we welcome resource persons, especially from the IALU network, and of course, collaborators who may be from outside the network, but who share the common goal of pushing sustainable development goals. And again, I want to thank my colleague, the director of the center, for supporting this initiative, and our dean and longtime host for, of course, organizing the technical details. Right, that concludes my brief remarks. I wish you find wish all of you a stimulating webinar today.
Thank you very much, Dr. Tan. To introduce our speakers, I would like to call on the Director of the Center for Engineering and Sustainable Development Research, Professor Alvin Colaba. Dr. Colaba, you're on mute.
Unmute from my end. Okay. Good morning, everyone. Good afternoon or good evening in some other parts of the world. Chancellor Emeritus Dr. Carmelita Kibenko, the President also of De La Salle University, Brother Bernie Oka, FSC, Brother Joe Scheiter, who is here with us, and other La Sallian brothers around the world, colleagues in the academe, guests, participants, ladies and gentlemen, good morning. The Center for Engineering and Sustainable Development Research is a host to this La Salle Sustainability Lecture Series. The center has been established back in 2003, where the center was primarily envisioned to undertake sustainability-related studies. And over the past 15 years or so, we have published over 7,000 or 8,000 scientific papers that you can find in the global literature. This morning here in the Philippines, we are again honored to have our lecture for this month, which relates to the food security issues using co-culture systems by intensifying production of crops and animal protein without requiring additional land area. This talk this morning show how a graph-theoretic optimization model based on ecological network analysis can determine robust co-culture strategies by controlling the presence of key species. Results of simulations on a hybrid rice and crayfish production system indicate that the comparable levels of productivity can be achieved with different ecological network structures. We are honored to have 2 distinguished speakers for this morning. We have the first speaker, Dr. Heriberto Cabezas. He's a professor of the Research Institute of Applied Earth Science at the University of Miskolc in Hungary. He retired as Senior Science Advisor, Land and Material Management Division of the US EPA in April 2019. He is past chair of the Engineers Forum on Sustainability representing all of the major professional engineering societies. His awards include 1998 US EPA Science Achievement Award in Engineering, 2007 Distinguished Alumni Achievement Award from the New Jersey Institute of Technology, 2011 Research Excellence Award in Sustainable Engineering from the American Institute of Chemical Engineers, and the 2013 Lawrence K. Cecil Award from the AICHE. Dr. Cabezas holds a PhD and MS from the University of Florida and a Bachelor of Science, magna cum laude, from the New Jersey Institute of Technology, all in chemical engineering. He served as a U.S. Embassy Science Fellow in Zagreb, Croatia in 2014. He's a fellow of the AICHE, a member of the American Association for the Advancement of Science, and a board-certified member of the American Academy of Environmental Engineers and Scientists. Dr. Cabezas is the co-founder of the Transatlantic Research and Development Interchange on Sustainability, or TARDIS, workshop series held biannually since 2003. He co-leads the International Work Group on Global Sustainability. His publications include over 100 peer-reviewed articles and chapters, 2 edited books, a US patent on electrochromatography, and 2 major softwares. His current research interests focus on 1, the design of sustainable processes and supply chains, 2, the development of models and policies for global sustainability, and 3, the study of pandemics as complex systems. Dr. Cabezas is a decorated US Navy veteran of the Vietnam conflict. He will be joined by another distinguished faculty here at De La Salle University. Dr. Angeline Lau is currently a full professor in the Department of Mathematics and Statistics and the Assistant Dean for Research and Advanced Studies of the College of Science at De La Salle University, Manila. She joined DLSU after the completion of her doctorate degree in Systems Biology at the University of Rostock in Germany. She obtained her BS and MS degree in Mathematics at DLSU. She is the current unit head of the Systems and Computational Biology Research Unit under the Center for Natural Sciences and Environmental Research, or CENSER. She held 2 professorial chairs in mathematics, namely the Brother C. John Leinan FSC Professorial Chair in Mathematics and the Brother Albinus Peter FSC Professorial Chair in Mathematics. Several of her most notable publications include her work on establishing mathematical and compartmental models to describe and analyze biological and signaling pathways associated to different diseases. She also applies mathematical and computational models to study epidemic spreading of diseases and health communication dynamics. Her recent works apply mathematics to study and discover the patterns in the topological structures of different networks and graphs. Ladies and gentlemen, let us welcome Dr. Cabezas and Dr. Lau.
Thank you very much, Dr. Colada. So first we will hear from our 2 speakers, and then we will have the Q&A portion after the presentations. However, in case you have questions, you may type them in the chat box during the presentation. Without further ado, I would like to give the floor to our speakers, Dr. Cabezas and Dr. Lau.
Thank you very much, Dr. Colava, for the kind introduction. A pleasant day to all. I am Angie Lau from De La Salle University, and together with me is Dr. Alberto Cabezas. Okay. We are excited to present our recent work entitled Maintaining the Productivity of Co-culture Systems in the Face of Environmental Change that has recently been accepted in Nature Sustainability. This work is done in collaboration with Dr. Kathleen Aviso and Dr. Raymond Tan.
Profesor Jenny de la Universidad de La Salle en Manila, las Filipinas. Estamos muy encantados de poderles presentar hoy nuestro trabajo reciente sobre el mantenimiento de la productividad de sistemas de ecocultivo frente al cambio ambiental que ha sido el artículo ha sido recientemente aceptado en Nature Sustainability. Gracias.
So this is the outline of our presentation. We'll start with the motivation of the study focus on co-culture systems and environmental changes. Then proceed with the methodology of the study and finally the main results that we publish in the paper.
Este es el esquema de la presentación. Comenzamos con la motivación del estudio enfocado en sistemas coculturales y cambios ambientales. Luego se procede con la metodología del estudio y finalmente los principales resultados que publicamos en la revista Nature Sustainability.
So let us start with the motivation of this study.
Bueno, comenzamos con la motivación del estudio. Next slide.
Feeding the world's population within sustainable land, water, and nutrient footprints is a daunting challenge. So as shown in the historical world population chart in this on the right upper right corner, so the increase of the human population grows exponentially in the last few years. So it is really an issue to feed the world.
Alimentar a la población mundial dentro de la capacidad sostenible de tierra, agua y nutrientes es un desafío enorme. Llamo su atención a la gráfica de la población mundial a través del periodo de historia grabado. Noten el aumento de la población reciente, como se muestra en el cuadro histórico. En los últimos años esto ha crecido, la población ha crecido exponencialmente y es realmente una cuestión de cómo alimentar al mundo entero. Gracias. Next slide.
So in addition to that problem, to keep pace with the growing demand, we also have the climate change that threatens the capacity of food production systems.
Además de este problema, tenemos el reto de la creciente demanda de alimentos y también tenemos el reto del cambio climático que amenaza con reducir la capacidad de los sistemas de producción de alimentos. Next slide.
And to address this, some researchers considered and saw the potential of using aquaculture of lower trophic level species to provide a larger share of future protein requirements. However, an issue that arises from this proposal is the sustainability concerns in the production of feeds and generation of organic pollutants from intensive aquaculture.
Para confrontar este reto, algunos investigadores han considerado y vieron el potencial de utilizar acuacultura de especies de niveles tróficos inferiores para proporcionar una mayor proporción de necesidades futuras de proteínas. Sin embargo, un problema que surge de esta propuesta es la preocupación por la sostenibilidad en la producción de alimentos y por el hecho de que la acuacultura intensiva puede llevar a la generación de contaminantes orgánicos no saludables. Next slide.
So in support of this effort, we propose to apply ecological engineering principles or models into hybrid agriculture, aquaculture, or it's called co-culture. So we propose to use ecological engineering principles or models to develop intensify food production system or process alleviating environmental footprints.
En apoyo de este esfuerzo, propusimos aplicar principios o modelos de ingeniería ecológica en agricultura y acuicultura híbrida, a lo que se llama cocultivo, propusimos utilizar principios o modelos de ingeniería ecológica para desarrollar sistemas o procesos de producción de alimentos intensificados que alivian las huellas ambientales de la producción de alimentos. Next slide.
Here we propose the ecological engineering principles that is a graph-theoretic optimization model. We present here the fundamentals of process graph or pgraph.
Y aquí propusimos los principios de ingeniería ecológica, que es un modelo de optimización de teoría de gráficos. Presentamos aquí los fundamentos del proceso llamado pgraph. No creo que haya una traducción a castellano de pgraph. Thank you. Gracias. Next slide.
For graph theoretical framework for process network, this is developed by Friedler, Fan, and many other colleagues. It is first designed and applied to chemical engineering for mass production of chemicals. Its advantage actually include computational efficiency and automated generation of alternative structures or networks. It has the capacity or capability to enumerate good, optimal, and near optimal options that is vital to effective problem analysis and decision support.
Los profesores Ferenc Friedler y L.T. Fan colaboraron y desarrollaron el marco teórico de los gráficos para procesos de redes. Primero se diseña y aplica a la ingeniería química para producción en masa de productos químicos. En resumen, inicialmente esto se aplicó a problemas de ingeniería química. Sus ventajas incluyen la eficiencia computacional y la generación automatizada de estructuras alternativas. Tiene la capacidad de enumerar buenas opciones óptimas o casi óptimas que son vitales para un análisis de problemas eficaz y de apoyo para tomar decisiones correctas. Next slide.
So the process graph is a bipartite graph. So a bipartite graph is defined as a graph that contains two sets of nodes. In this case, it consists of M-type node and O-type node. Okay. The M-type node are the ecosystem services, and the O-type node are ecosystem functional units. And M-type nodes are represented in circles, O-type nodes are represented in rectangles. Okay. It performs a combinatorial search of feasible socio-ecological networks or systems. The arcs that we have here indicate interactions between the ecosystem services and ecosystem functional units. So inputs to the O-type nodes, like this, indicate ecosystem services necessary for the survival of this ecosystem functional units. In this example, it's the plant. Okay. So some ecosystem services can be classified as exogenous or terminal. For exogenous, these are ecosystem services originating from outside of the ecosystems, for example, raw material here. And terminal ecosystem services exist in the ecosystems for human use, for example, and they're usually regarded as the final product of the ecosystems. In this case, this is the terminal ecosystems or final product in the systems.
El gráfico de proceso es un gráfico bipartito que consta de un nodo de tipo M, servicios del ecosistema, y un nudo de tipo O, unidades funcionales del ecosistema, que satisfacen los 5 axiomas que se mostrarán a la siguiente diapositiva. Realizada la búsqueda combinatoria de redes o sistemas socioecológicos, los arcos indican interacciones entre los servicios de los ecosistemas y las unidades funcionales de los ecosistemas. Las entradas a un nodo tipo O indican los servicios ecosistémicos necesarios para su supervivencia. Algunos servicios de los ecosistemas pueden clasificarse como exógenos, es decir, que se originan fuera del ecosistema, o terminales, es decir, que salen del ecosistema para uso humano. Este último puede considerarse como el producto final del ecosistema. Next slide.
Okay, so these are the core actions needed when we establish a process graph. So these are the core actions that need to be satisfied. The first one, there should be a terminal ecosystem services. That means the final product should be defined in the P graph. Okay. For the second one, an ecosystem service is exogenous if and only if it is not an output of a functional unit defined in the ecosystem structure. So for example, the solar energy, it should not have any inflow, okay, to it. Third one, only those ecosystem functional units that are defined in the ecosystems can appear in an ecosystem solution structure. So the subnetworks that will be generated from existing P graph or should all the elements in the subnetwork or subgraph should be part of the superstructure. Okay. Fourth one, an ecosystem functional unit has at least one path leading to a terminal ecosystem services. The action ensures that all functional units are non-redundant, but are directly or indirectly involved in the generation of final product. This simply means that there's always a way you can lead to or go to the final product from the given nodes. Okay, there's always a connection. And then the last one, if an ecosystem service belongs to the ecosystem structure, it must be an input or output from at least one ecosystem functional unit represented in the structure. This means that there should not exist a node that does not have an inflow or outflow. So there should be no floating nodes in the defined P graph. So these are the criteria in establishing a P graph.
Los axiomas centrales son 5 de ellos. El primero dice, debe existir un servicio ecosistémico terminal. Quiere decir, el ecosistema debe producir algo útil, desde el propósito humano, por supuesto. Un servicio ecosistémico es exógeno si y solo si no es un producto de una unidad funcional definida en la estructura ecosistémica. Quiere decir, tiene que entrar de afuera. Solo aquellas unidades funcionales del ecosistema que están definidas en el ecosistema pueden aparecer en una estructura de solución del ecosistema. En resumen, las unidades que se definen son las que componen el ecosistema. Cualquier unidad funcional del ecosistema tiene al menos un camino que conduce a un servicio del ecosistema terminal. Quiere decir, tiene que tener algún propósito. Este axioma asegura que todas las unidades funcionales no sean redundantes, pero que estén directa o indirectamente involucradas en la generación de un producto final. El quinto, si un servicio del ecosistema pertenece a la estructura del ecosistema, debe ser una entrada o salida de al menos una unidad funcional del ecosistema representada en la ecoestructura. No debe existir un nodo que no tenga una entrada o salida. Quiere decir, cualquier nodo tiene que estar conectado al sistema para pertenecer allí. Gracias. Next slide.
So to analyze a P graph, the software P Graph Studio is used, and it is developed at the University of Pannonia in Hungary. It is actually available free of charge for research purposes via the link here, p-graph.org.
El software P Graph Studio se desarrolló en la Universidad de Pannonia en Hungría y está disponible, accesible de forma gratuita para fines de investigación a través de el enlace en el web pgraph.org. Next slide. Next slide.
Okay. In this, oh, sorry. Okay. Now it jumped. Okay, so in this slide, we illustrate the socio-ecological systems presented as p-graph in the middle, and using the optimization algorithm to generate one sample combinatorial feasible subnetwork of the given socio-ecological system. Okay, so the mass or energy is defined, and this will be available to keep the ecosystem structure functioning. And these parameters are used to meet the ecosystem services goal, that is, in most cases, to minimize the cost metrics. This can be defined as the money or ecological footprints and some other metrics. Okay. We present in the next few slides the component algorithms to meet this ecosystem services goal.
En esta diapositiva ilustramos un sistema socioecológico presentado como un gráfico P en el medio de p-graph, y usamos el algoritmo de optimización para generar una subred combinatoria factible del sistema socioecológico, dado la masa y energía se define y están disponibles para mantener la estructura del ecosistema en funcionamiento. Quiere decir, deben existir suficientes recursos para mantener el sistema funcionando. Estos parámetros también se utilizan para cumplir con la meta de servicios ecosistémicos, es decir, minimizar las métricas de costos como dinero, huella ecológica, etc. En las próximas diapositivas presentamos los algoritmos componentes para cumplir con estos objetivos de servicios ecosistémicos. 3 gráficas, la estructura máxima, una subestructura y una gráfica. Thank you. Next slide.
So for the component algorithm, first we present the maximal structure generation, or MSG algorithm, that generates a network which is the union of combinatorically feasible networks. So as you can see, it determines the structure that contains all possible networks, and the result is an error-free superstructure. So on the right, we have the superstructure of the socio-ecological system defined in the previous slide.
Primero presentamos el algoritmo de generación de estructura máxima, que consiste de la unión de todas las subestructuras, que genera una red que es la unión de todas las redes combinatorias factibles, como ya he dicho. Determina la estructura que contiene todas las redes posibles. El resultado es una superestructura libre de errores. En el lado derecho tenemos la superestructura del sistema socioecológico presentado en la diapositiva anterior. Next slide.
Okay. Next, we present the solution structure generation, or SSG algorithm, that is capable of generating all combinatorically feasible networks based on the enumeration of possible structures arising from the relationships that we defined in the ecosystem service in the system, which includes the ecosystem services and ecosystem functional units. So it defines basically the combinatorially feasible subnetworks of the maximal structure.
A continuación, presentamos el algoritmo de generación de estructura de solución, SSG en inglés son las siglas, que es capaz de generar todas las redes combinatorialmente factibles basadas en la enumeración de posibles estructuras que surgen de las relaciones entre los servicios del ecosistema y las unidades funcionales del ecosistema. También identifica subredes combinatorialmente factibles de la estructura máxima. Thank you. Next slide.
Okay. So including the maximal structure, these are the 20 different p-graph structures that are generated from the given system. Each of these subgraphs or feasible structures define different ecological systems giving different cost metrics. And one may choose the ideal setup and optimal cost metrics accordingly from the proposed feasible structures.
Incluyendo la estructura máxima, estas son 20 estructuras de gráficos pgraph diferentes que se generan a partir de un sistema dado. Quiere decir, dado un sistema, estas son las gráficas factibles. Cada uno de estos subgráficos, subgrafos o estructuras factibles definen diferentes sistemas ecológicos, dando diferentes métricas de costo. Uno puede elegir la configuración ideal y las métricas de costo óptimas en consecuencia de las estructuras factibles propuestas. Next slide.
So for the MSG and SSG algorithm that are shown earlier, those focus on network connectivity and do not account for transfer between units. So the flow rates, and if we assign also parameters or values to these nodes. The accelerated branch and bound ABB algorithm is used to determine optimal and near optimal structure, enhanced with the SSG algorithm by evaluation of the performance of the candidate networks, as shown here, and by eliminating infeasibility and redundant solutions. So as shown in the illustration, the defined flow rates in the process graph are used to compute for the corresponding, for example, final production, the amount of crayfish that we will produce in the network or system.
Okay. Give me 1 second because, okay. Nos enfocamos en el MSG y SSG sobre la conectividad de las redes que toman en cuenta la transferencia entre las diferentes unidades. Se utiliza el algoritmo ABB, en inglés Accelerated Branch and Bound, para optimizar el sistema y obtener redes óptimas o cerca de óptimas, cosa que se puede evaluar el comportamiento, la producción de los diferentes redes propuestas. Como se ha demostrado en la ilustración, se requiere que se definan los flujos dentro de la red del sistema y el algoritmo MSG, SSG no toma en cuenta transferencias entre unidades, sino que la estructura. El algoritmo ABB es el que optimiza el sistema tratando de generar estructuras óptimas o casi óptimas, como se ha enseñado en la ilustración. Gracias. Thank you. Next slide. Next slide.
Yes.
Okay.
Okay. Lastly, we show how robust strategies are generated to address food securities and intensify the production of crops without additional land area using process graph.
Por último, mostramos cómo se generan estrategias sólidas para proporcionar la seguridad alimentaria e intensificar la producción de cultivos sin área de tierra adicional usando un gráfico de proceso o un pgraph. Next slide.
So here we illustrate the use of pgraph on social ecological systems via this case study. So in this co-culture system, it simultaneously produces rice and crayfish using the same land area without an external supply of supplements. So the diverse ecosystems embedded in the farm includes, for example, aquatic plants, okay, some aquatic plants, phytoplankton, benthic animals, and zooplanktons. Okay. in this co-cultural system, the crayfish is the system. So the crayfish in the system can eat, okay, some of these. So when we have the food here, that means these are the food sources of crayfish in this defined ecosystem. Okay. So this includes, for example, snail, aquatic plants, rotifera, copepoda, and also rice, okay, which is actually another final product being harvested by the farmer in this ecosystem. And other more food connected to crayfish, okay, these are some other foods, okay. And then in this ecosystem, for example, you can see that Cladocera here, okay, aside from being a food source for crayfish, it also competes. Okay, it also competes with crayfish by eating rotifera, bacterioplankton, and etc. So the purpose of this modeling this co-culture system using pGraph is to identify robust, optimal network or systems that maximize the system's productivity per unit plant area. And this is if the co-culture system is designed to maintain the yield of primary crop like crayfish and rice. Okay, the productivity can also be measured in terms of the crayfish-rice ratio, which is what we did in this study.
Ilustramos el uso del gráfico P en sistemas socioecológicos a través de un estudio de caso específico. El sistema de cocultivo produce simultáneamente arroz y camarones de agua dulce, utilizando la misma superficie de tierra sin un suministro externo de suplementos. El ecosistema diverso incrustado en esta granja de producción incluye plantas acuáticas, fitoplancton, animales bénticos y zooplancton. En este sistema de cocultivo, los caracoles del sistema pueden comer caracoles, plantas acuáticas, rotíferos, copepodos, arroz, que son los otros productos finales que se cosechan, los agricultores en el ecosistema, y otros alimentos más relacionados con los camarones de río. En este ecosistema, Cladocera compite con los camarones de río al comer rotíferos, bacterioplancton, etc. El propósito de este modelo es identificar redes robustas óptimas que maximicen la productividad del sistema por unidad de área de tierra. Es decir, si el sistema de cocultivo está diseñado para mantener el rendimiento del cultivo primario, la productividad también se puede medir en términos de relación al camarón de río, al arroz o al arroz. ¿Qué es lo que hicimos en este estudio? Quiere decir, en este estudio pues se buscó la forma de optimizar la producción del sistema en términos de camarones de río y de arroz. Thank you. Next slide.
So simulations were performed to maximize crayfish production per unit of rice. And solving the model generates 60 alternative optimal and near optimal solutions from these maximal structures. That contains all the possible network linkages defined in this co-culture system. Note that differences in productivity result from varying distribution of nutrients within these structures. So we did not show the 60 structures, but just believe us that we generated 60 sub-networks or alternative optimal and near optimal solutions.
Se realizaron simulaciones para maximizar la producción de camarones de río por unidad de arroz. Resolver el modelo genera 60 soluciones alternas óptimas o casi óptimas a partir de una estructura máxima, que de nuevo es la unión de todas las superestructuras, que es nuestra dispositiva, que es esta diapositiva, que contiene todos los vínculos de las redes posibles. vínculos de las redes posibles. Tenga en cuenta que las diferencias en la productividad resultan de la distribución variable de nutrientes dentro de estas estructuras. Thank you. Next slide.
So from the sixth structure, we'll just present some to highlight how this approach can be applied to study the co-culture system or propose a better strategy in designing this co-culture system. So here we show that with this visible structure, it provides optimal production of around 0.8 kilogram of crayfish per kilogram of rice. Okay? So the optimal harvest can be obtained with this cartoon or this component in the co-culture systems that include the aquatic plants, rice, phytoplankton, and detritus as food sources for crayfish. Okay? And the network you will see if you compare the P graph, excluding the shaded parts in gray, okay, this P graph is now, or this network is now much sparser than the original superstructure.
Aquí mostramos que con esta estructura factible se proporciona una cosecha o producción óptima de alrededor de 0.8 kilogramos de camarón de río por kilogramo de arroz. La cosecha óptima se puede obtener con un suministro fijo supuesto de plantas acuáticas, arroz, fitoplancton, de detritos y detritos como fuentes de alimento para los camarones de río. La red es mucho más dispersa que la máxima, cuya estructura se puede ver en las partes sombreadas de la figura. Las conexiones más en gris. Thank you. Next slide.
So aside from the food sources defined in the optimal structure that we see in the previous slide, okay, we have additional species included here, that is Rotifera, benthic bacteria, and bacterioplankton as food sources for crayfish. But with this additional food source, the harvest of crayfish is reduced by a very small difference to 0.79 kilogram crayfish per kilogram of rice. So what we want to highlight here, what is interesting about this is we have more food sources for crayfish, but that does not imply more production of crayfish. Okay? This may be due to some unobvious competition that happens in this co-culture system for the food supplies that are actually observed and integrated in the P-graph algorithm.
Aparte de las fuentes de alimento definidas en la estructura óptima, esta estructura también incluía rotíferos, bacterias bénticas y bacterioplancton como fuentes de alimento para los camarones de río. Con estas fuentes adicionales de alimentos, la cosecha de camarones de río se reduce un poco por una diferencia pequeña, alrededor de 0.79 kilogramos de camarón de río por kilogramo de arroz. Curiosamente, tenemos más fuentes de alimento para los camarones de río, pero esto no implica una mayor producción de camarones de río. Esto puede deberse a alguna competencia no obvia de suministros de alimentos que ocurren en el sistema de cocultivo, que en realidad se observan e integran el algoritmo de P-graph. Aparte de las fuentes de alimentos definidas en la estructura, esta estructura también incluía rotíferos, bacterias bénticas y bacterioplancton como fuentes de alimento para los camarones de río. Con estas fuentes adicionales de alimentos, la cosecha de camarones de río se reduce un poco por una diferencia pequeña, como se ha dicho, probablemente porque haya competencia entre las diferentes fuentes de alimento. Thank you. Next slide.
So here we have the summary of how the behavior of the 60 structures generated with the corresponding number of crop production, okay, productivity of these 60 feasible structure. So the results shown here, okay, in the previous two slides suggest that optimality of crop production is not necessarily correlated to the number of species in the co-culture system. So here we show the trends with changing ecosystem structure against the number of species presented in the productivity based on the mass of crayfish per unit of rice. So with the latter being a proxy for land area, as we mentioned earlier. So the key result is that there are families of ecosystem structure that differ in the number and type of biological species, but have nearly identical productivity. For example, you can see here that structure 1 to 4 have similar levels of productivity that is approximately 0.12 kilogram of crayfish per kilogram of rice. But the number of species in blue, okay, varies from 5 to 9. Okay, so the level is from 5 to 9. They change as they are not actually, they don't have the same number of species. These are biologically different ecosystems, but are similar with similar productivity. So these are several sequences of families of structure where the productivity is robust and varies minimally if the species present in the also present significantly changes.
Los resultados que se muestran en las dos diapositivas anteriores sugieren que la optimización de la producción de cultivo no está correlacionada con el número de especies del sistema de cocultivo. Aquí mostramos las tendencias con la estructura cambiante del ecosistema frente al número de especies presentes y la productividad basada en la masa de camarones de río por unidad de arroz, siendo este último un indicador indirecto del área de superficie que se utiliza. El resultado clave es que hay familias de estructuras de ecosistemas que difieren en el número y tipo de especies biológicas, pero tienen una productividad casi idéntica. Por ejemplo, las estructuras de número 1 a 4 tienen niveles similares de alrededor de 12 kilogramos de camarón de río por kilogramo de arroz, pero el número de especies varía de 5 a 9. Estos son ecosistemas biológicamente diferentes, pero con una productividad similar. Hay varias secuencias o familias de estructuras donde la productividad es robusta y varía mínimamente cuando las especies presentes van cambiando. También quiero mostrar las estructuras del 5 al, me parece que es al 15. Thank you. Next slides.
Okay. So to summarize and conclude our work, our results demonstrate how the analysis of alternative network structures can be used to ensure productive co-culture systems. And rather than identifying a unique optimum, the process graph approach is used to identify families of solutions, which translate into options that give good productivity while being robust to disruptions. And these solutions provide guidance on management of co-culture operations, but in practice, controlling species might actually require more future work. And such information can be used to guide future agronomic co-culture field experiments by identifying potential favorable system configuration, for example, the given surface area. And this can also be used to guide in farming for guidance for farming practices.
Nuestros resultados demuestran cómo se puede utilizar el análisis de estructuras de red alternativas para garantizar sistemas productivos de cocultivo. En lugar de identificar un óptimo único y posiblemente frágil, el enfoque de gráficos de procesos o PIGRAPH se utiliza para identificar familias de soluciones que se traducen en opciones que brindan una buena productividad y son resistentes a las interrupciones. Estas soluciones brindan orientación sobre la gestión de las operaciones de cocultivo, pero en la práctica el control de las especies presentes requeriría mucho más trabajo de investigación. Dicha información se puede utilizar para guiar futuros experimentos de campo de cocultivo agronómico mediante la identificación de configuraciones de sistemas potencialmente favorables, por ejemplo, dada una superficie, y prácticas agrícolas. Quiere decir, el estudio ha identificado las posibilidades que pueden existir, pero requiere un poco más de trabajo para realizarlas en práctica. Thank you. Next slide.
Thank you for listening.
Thank you for listening. Thank you very much y muchísimas gracias por escuchar y por su atención.
Thank you very much, Dr. Cabezas and Dr. Lau, for that very interesting and relevant presentation on the application of P-graphs on co-culture systems. Actually, I have read Dr. Cabezas' earlier works on P-graphs before meeting him today, and I can say that P-graph is a really powerful tool that can be used for sustainability. And now we are moving to the Q&A portion of our program. I would like to invite the audience to raise your questions to our speakers. You may type your questions on the chat box, or you may unmute yourself and direct your questions to our speakers. Okay, let me check the chat box. I'll start with the first question. What are the criteria for prioritizing, choosing, identifying which co-culture of plant and animal systems can result to a good production?
Angie, you want to start?
Can you repeat the question? Sorry, I was looking at the chat box.
Okay, so this is the question. What are the criteria for prioritizing, choosing, identifying which co-culture of plant and animal systems can result to a good production?
Okay. As mentioned in the talk, the feasible structures are generated using the P-graph algorithm. So the P-graph computes how to optimize the production of the crayfish and propose what should be the feasible system or structure that will generate that corresponding optimal production of crayfish. So it's not us who's actually deciding, okay, which system will give an optimal production of crayfish. It's computed or simulated using the algorithm. Okay, it tries to optimize the production of crayfish, and based from the optimal production, you choose and you can decide which one is feasible or the one that you can actually set up in your own farm or setup.
Okay, thank you very much, Dr. Lau. So, are there any questions from the audience? Maybe you can raise your hand and unmute yourself. How about, did you consider the types and volume of wastes that can be generated in the systems with the different ecological structures?
Oh my God.
Say something to that. Well, what language do you want me to respond in?
You can do both.
Yes.
I can't do both, but you can do both.
I think English is fine though.
English is okay. Okay. Yeah, the idea here is that the crayfish can eat almost anything. So a lot of the material that might be waste that you need to deal with, the crayfish simply eats. So it simplifies the problem. Just in case, I'll mention it in Spanish. La idea es que el camarón del río se lo come casi todo. Entonces esto simplifica la dificultad de qué hacer con los desperdicios que puedan generarse. Yeah, that's it.
So it means that there is very minimal waste that being produced because the crayfish consumes the waste. So it's really a sustainable system. Have these network configurations been tested or experimented on or validated on actual production systems, or do you have any plans to partner with farmers to test the configurations and validate the models?
We actually now collaborated with biologists from our university, and they are giving us more fields, their experience in the fields, and giving us more of their expert opinion on how reliable is the model, or the more reliable parameters to be used in the model. And in the future, I think that can also be applied, as strategies proposed to them, how they can control and manage their ecosystem or aquaculture system.
Thank you, Dr. Lau.
I think Roberto wants to add something.
So it's right if we step on each other occasionally, as long as we don't do it too often. This study, I should point out, was done on data from a real aquaculture system. It is not a model. I mean, somebody actually ran this system and collect data on it. So, so we are fairly confident that these results are reasonable, because it's not just an abstract model. It's actually using data from a real life system. But more work is needed. That's clear.
Thank you, Dr. Cabezas and Dr. Lau. There is a question in the chat box from Miss Maria Edda Apple Supido. Is PGraph accessible, or this needs subscription? A potential need to train to use the application? So do we need subscription to use PGraph, and is there training needed?
It's free.
It's free.
Do you need training? Yes. The software is free, but yeah, you do need, and there is training online. The people at the University of Pannonia have training modules, I believe, and even a video that you can watch. And Angie, I don't know what else you want to add.
And I think once in a while, Dr. Aviso, Dr. Tan, they also organize workshop for PGraph. So maybe you should stay tuned and watch out for the workshop that they will be organizing.
True.
Is it easy to learn PGraph? It depends on the determination of the person.
Use it very often, it's very easy to use. But since PGraph, as I mentioned earlier in the talk, that it's designed originally for chemical engineers. So currently, the platform of PGraph is all the units of measurements are related to engineering or manufacturing related stuff. So it's not yet defined in terms of socio-ecological network or aquaculture system. So you have to make your own interpretation or conversion when you're designing the PGraph system for socio-ecological or aquaculture system.
So with regards to that, will there be a danger of being biased? Say, if we use a certain data from a certain farm, so will it be limited to that specific scenario, or if we can still apply the models to other scenarios. So how do we, what is your thought about the biases that arise from the P-graph?
Roberto, do you want to?
Yeah, no, I think these results are fairly general. The main thing that they give you is structures, and that's fairly general. I don't think this is specific to just one particular situation. No. And
Maybe to add, actually, that's what you actually do with models. You try to also tune the parameters. And by tuning the parameters, you will know the appropriate setup or setting that you need to control or manage the ecosystem or the co-culture systems that you have. So by tuning the parameters also helps in proposing or suggesting strategies how we can better manage the co-culture system.
Okay. So there is another question from Miss Maria Eda. Will this provide site-specific recommendations and interpretations? I think this is related to the question earlier.
Roberto, do you?
Okay. Yes, it can provide site-specific recommendation. However, models are not reality. Models are simplified versions of reality that you use to guide your thinking and to get you to know what is important, what is not important. So you can use it for a site, but as a precaution, you always do a little bit of a test to make sure that the model is on track. I have been dealing with models for longer than many of you have been alive. And I can tell you that models are wonderful tools. Look, we all have a model inside our heads, whether we believe it or not. I know that if I do if I drink some water, it will quench my thirst, because I have a model inside my head that tells me that it works, and it goes on from there. But you have to be careful with the fine details. The model helps you, guides your thinking, tells you what's important, what you may want to try, but just treat it with a little bit of respect, because models are not reality.
Yes. I'm reminded of the quote that all models are wrong, but some are useful.
Exactly.
Okay, there's another question from Professor Biswajit Sarkar. Professor Sarkar, do you want to unmute yourself and direct your questions to our speakers?
During the solutions,
Hello?
did you consider all basic properties of basically it's defined as a bipartite graph. So the M-type nodes and the O-type node, they don't belong to, so that you cannot find an arcs connecting the O-type nodes, or you cannot find any arcs connecting the M-type node. So the arc should be from O-type to M-type or M-type to O-type. So yes, the bipartite properties are being considered when we generate the algorithms.
Okay, that is thank you very much.
Thank you, Dr. Sarkar. Okay, any more questions from the audience?
Maybe I can make a further elaboration on the question a while ago about the interpretation and recommendation. So, for example, you have from the 60 structures that are generated, for example, there are some structures that has similar productivity index. Okay, but these are different structures. So if you're the farmer, one possibility is you may choose among all of these structure what are the species that exist in your farm. Okay, and with this species that exists in your farm, you know that what are the possible or the projection of the productivity. And if you want to improve your productivity, maybe one of the structures said that you have to remove this species in your ecosystem or in your co-culture system. So that means that to improve your productivity, you might need to figure out how to remove this specific species in your co-culture system, or what other species you need to add in your co-culture system in order to improve or increase the productivity. So I think those are the types of recommendation or interpretations that you can do using process graph.
Exactly correct, yes.
Thank you, Dr. Lau, for the elaboration. Okay, any more questions from our audience? How will the research support the fight against climate change? Can you discuss a little bit about its relation to climate change, since it's a very relevant issue that we have right now?
This kind of work says that there are families of ecosystem structures which are productive even though the component species are changing. And the hope is that if climate change occurs, well, it seems to be occurring as best as we can tell, and the species in your co-culture system begin to change. If you're lucky enough, if you've managed to be in one of the families that has high productivity, you can endure quite a bit of change and still maintain good productivity. So we're looking for basically it demands to a resilient co-culture system, one that doesn't lose too much productivity if you have a change in the number of species, which is what's likely to happen if it gets warmer or colder. So maybe Professor Lau may have more to add.
So it's
I think
a
that's
robust.
it.
Yes, Dr. Lau.
I have nothing to add.
Okay. I think we can hear from Professor Raymond Tan regarding P graphs. He has some thoughts about P graphs.
I'm sorry to step in like this. I know the stage is yours, but there was a query earlier today about PGraph, and we're certainly happy to say that we have significant expertise at De La Salle University to conduct PGraph training if we know that there's a demand for it. So if there's anyone in the audience who represents an institution where there might be significant interest in a workshop, which is more than just a webinar, but a tutorial for, let's say, 6, 8, 10 people, we can talk about that and organize it as part of joint initiatives. Thank you for that.
Yes, absolutely.
Thank you, Dr. Tan. So before we end our lecture today, allow me to share my screen so that I can invite you to the next lecture, which will be next month. So next month, our topic would be Vida Natural Project, Mechanism for the Carbon Neutral Declaration of the Huetar Caribe Regional Unit, National Institute of Learning of Costa Rica from the period 2016 to 2020. And our speakers are Asdrubal Bustos Valdelomar and Sebastian Miranda Brenes from the National Institute of Learning Costa Rica. Please don't forget to register to our event using the link or by scanning the QR code on the screen. So this will be next month on June 29 at 8 a.m. Philippine time. And this lecture will be in Spanish but will be translated, just like our lecture today. And please do not forget to evaluate our lecture today using the link and or scanning the QR code on the screens. Any final words from our speakers for today?
Well, it's been an honor and a great pleasure to be part of this lecture series. And I hope the translation to Spanish was helpful, at least to some of the audience. I have one confession to make. There was one particular slide where I think I wrote notes of what I wanted to say in Spanish, and I realized the Spanish notes are missing, so I had to translate from English as I went. So if it seemed a little bit halting, that's because I was simultaneously translating, but I think it came out okay. I hope so. So thank you very much to everyone.
And thank you everyone for joining us today. And thank you to our speakers for sharing and giving your time in sharing your research. Very relevant and interesting. Once again, I would like to thank the audience this morning, and I hope you will enjoy the rest of the day and the rest of the week. Stay safe and healthy, and we will see you on the next lecture. Thank you very much. Bye-bye. Oh, by the way, how about a photo with the panel? Maybe the four of us can take a photo. And for the remaining audience, may we invite you to open your video later for a group photo. Okay, let me take the picture. Ready? 1, 2, 3. Smile. Okay. And then let's take a photo with the audience. How do we remove the spotlight?
I'll help you remove the spotlight.
Okay, thank you. All right. Okay, so now it's in gallery view. May we invite the audience to please open your videos and take a group photo with us. Okay. First page, smile, 1, 2, 3. Okay, second page. There are 3 pages. Okay, smile. And then last page, smile. Okay, thank you very much, and we'll see you next month. Please don't forget to register. Goodbye.